morning, Honors Math 3. Today is Tuesday, March 17th, 2020. You should have printed off the notes for today, Task 7-1, Day 2. Hopefully you're celebrating with us at home. Today is Tuesday. Go green. Hopefully you're celebrating with us. Alrighty, my recorder is 15 minutes long. That's how much I can record, so I will have that as my goal every day. 15 minutes or less. No guarantees today. These first two examples are just review from yesterday. Write the nth term of that sequence. We're talking patterns of numbers. So that's written a sub n is equal to. I'm going to give you a moment to look at that. It's an alternating sequence. Starts negative to positive, negative to positive. So as a hint, it's an alternating sequence. Try to write a formula for the nth term and then pausing. Okay, when I plug in 1, I get a negative fraction. When I plug in 2, I get a positive fraction. So if I use that alternating pattern, I think it's safe to just plug in n, because my first term wants to be negative. My second term, squared, should be positive. It's always a 1 over. Plug in 1, I get 4. Plug in 2, I get 5. Plug in 3, I get 6. I'm taking the term number and adding 3. And I would write my general term as that. Could you list the first 5 terms of this recursive sequence? I'm going to give myself a little space. A sub 1 starts at negative 2, a sub 2, a sub 3, a sub 4, and a sub 5. A recursively defined function or sequence tells you where to start at negative 2 and then tells you what to do using a previous term. So the second term, my index is 2 is my input. I'm going to input 2, then I'm going to add to it 3 times that previous term. Before a sub 2 is a sub 1, I'm going to plug in a negative 2 and see what I get. Please list the first 5 terms as review of that recursive. Okay, check your work if you would. Third term, plug in 3 plus 3 times the previous. I get negative 9. Plug in 4 plus 3 times the previous, negative 23, and a sub 5. And you can check your work. Alrighty, pause anytime you need to. Not only is it important to be able to describe a sequence or a pattern, it's also important to be able to find the sum of a sequence. When we need to add the first n terms of a sequence, we write it this way. The notation is find the sum of this sequence from some starting number, k equals 1, let's say, to our ending number, which is n. Find the sum of the terms of the sequence starting at a sub 1 and ending at a sub n for this sequence. Why the change to a sub k? The integer k is called the index of that sum, and the index, that k value, tells you where to start your sum and tells you where to end your sum. For example, just to expand a sum so you can see it, find the sum, counting, that's my counter, that's my index from k equals 1 to n of this sequence. Would look like starting at 1, 2/3 to the 1, plus 2/3 to the 2, k is my counter, plus 2/3 to the third, all the way up to 2/3. This tells me where to end at some number n. If I expanded this sum, now my index starts at 4, from k equals 4 all the way up to n. So I'm going to start my count at 4. That index, that counter, would be negative 1 to the 4 plus 1 times 2 to the, starting at 4, plus, keep going, negative 1 to the 5 plus 1 times 2 to the 5th, all the way up to, tells me when to stop at some number n, negative 1 to the n plus 1 times 2 to the n. Notice that's my general term, but I stop at the end. We could go the other way just to get comfortable with the notation. Use summation notation to describe this sum. First term is 1 all the way up to 2 times 12 to the negative 1. That must be my ending index. So I could rewrite that, condense it a little bit with a sum from k equals 1 to the ending point 12. Looks like I'm plugging into a pattern 2 times k minus 1. That counter, I use that k to go from 1 all the way up to that ending point n. What is the sequence? I could rewrite it as the sum of my index from k equals 1 to n. Looks like I'm always taking that number a, that constant a, and I'm plugging in r, second term, r to the first, third term, r to the second, nth term, that must be r to the k minus 1, and we can condense. If you have specifics starting and ending rather than just n, you could find the sum of the sequence from 1 to 6. Let's expand that if we could. So that is 5 times starting at 1, 1 squared, plus 5 times plugging in k, 2 squared, plus 5 times 3 squared, plus all the way up to 6. I'm going to pause and expand that. Go ahead. Expanded, that sum looks like this, from starting at 1 to 6. I notice I have a 5 in each of those terms. I could factor out a 5 and then write this as 5 times 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared. So really that means I could have factored out that 5 from that sum right away. We're going to see this when we turn the page. So this is the same as 5 times the sum from k equals 1 to 6 of k squared, of just squaring numbers. That's a property we'll see in a minute. Just as a little practice, please find this sum. Starting at 1 to 3, what does that mean? Just plug in 1, add it 2, plug in 2, add it 2, add 3. What's that, 6? Find the sum, I'm going to say, of the first 5 integers. Expand that and find the sum, please. So I'm going to say that's the sum of the first 5 integers. Those counting numbers, which is 15 if you add those up. Find the sum of the first 8 integers. Expand and find that sum. I'm going to expand and find the sum, and then I'm going to see if you can see a pattern. Some of you can start to see a pattern here. It's an important one. All right, just food for thought. When I plug in 3, I get a sum of 6. When I add the first 5 integers, I get a sum of 15. Sum of the first 8 integers is 36. We're going to prove this in a second. When I add the integers from 1 to n, the integers, watch this. I can always take this integer, this ending point, n, multiply it times n plus 1, 8 times 9, what's that, 72, 5 times 6, n plus 1 is 30, 3 times n plus 1, 4, which would be 12, and divided by 2. We're going to prove that in a second. All right, turn the page if you would. Thanks for working through. Oh, there's some properties of summations as we're getting used to the notation. If I have two different sequences, a sub n and b sub n, and some number, c is just some constant. You like that word, constant? Let's see. This is equivalent to, I can take that constant out. We saw that on the previous page. So these two things would be equivalent. I can always take a constant out. If I'm finding the sum of sequences and there's a sum inside that summation notation, I can separate that. So this is equivalent to these two sums by themselves. K equals 1 to n of a different sequence, b sub k. If I have subtraction inside a sum, I can separate that from k equals 1 to n of that first sequence minus the sum from k equals 1 to n of that second sequence. So there's some properties of some summations that we'll use in a minute. What if my index does not start at 1? If my index does not start at 1, some other number up to n, I could find the sum from 1 to n of that sequence and then get rid of the part of the sum I don't need, which would be from k equals 1 to the number just before this. Just before j plus 1 is j. We'll use that in a second, but think about that. So if you start at 5, you could find the sum of the terms from 1 to n, and then subtract off the 4 you don't need, 1 to 4, if that starting point was 5 instead of 1. We'll come back to that. Alrighty, here's a couple important sequences. I like to look at them before I prove them. This just says if you just find the sum of n constants, the sum of n constants for whatever that constant c is, what is that? That's the sum of c plus c plus c. And how many c's am I going to add up? Nope. From 1 to n is n c's. If I add a constant n times. What is that sum going to be? Keep adding a constant n times. That's just c times n. So if you ever find the sum of a constant, it's just c times that ending point. All right, again, this says the sum of the first n integers. That's what we just saw on the previous page, that pattern, the sum of the first n integers. Here's a proof of that pattern that we saw, or that formula that we saw. I'm going to add 1 plus 2 plus 3 plus, and I'm going to keep adding all those up, all the way up to, I'm going to call this n minus 2, getting closer, n minus 1 term plus n. All of those integers up to n. Watch this cool trick. I'm going to start lumping them together. Look at this. That's n plus 1. If I add those two terms, it's actually n plus 1 again. If I add these two terms, that is actually n plus 1 again. How many of those n plus 1s am I going to have? The number of terms divided by 2, since I'm lumping them in pairs. And I get that formula we just saw on the previous page. The sum of the first n integers is always n times n minus 1 over 2. We're going to use these in a minute. I call this the sum of the first n integers squared. What's 1 squared plus 2 squared plus 3 squared plus 4 squared, all the way up to that last ending index squared. This formula we might just have to memorize. It is n times n plus 1 times 2n plus 1 all over 6. I'm going to use it in a second. We'll practice that a little bit. We see it on your homework too. What's the sum of the first n integers cubed? These are a few fun formulas to be familiar with. That's 1 cubed plus 2 cubed plus 3 cubed plus all the way up to n minus 1 cubed plus n cubed. The sum of the first n integers cubed is a nice little formula, n times n plus 1 divided by 2 squared. Looks similar to that previous one. Let's practice those just a little bit. Alrighty. Alright, let's practice a few of those properties up above for some sums. I want you to find the sum of the first 26 terms in that sequence. That's challenging. Let's use some properties to make our life easy. I've got subtraction, so I can separate this. K equals 1 to 26 of this sequence minus the sum from k equals 1 to 26 of this simple sequence. But there's a coefficient, so I can take that out. That's 3 times the sum of k equals 1 to 26 of the first 26 integers minus, that's just a constant. So a constant times the number of constants I'm adding up. There's a formula up above for the sum of the first 26 integers. How is this formula? So I'm going to use that. Alrighty, so let's plug in, and that is 3 times n, 26, times n plus 1, 27, divided by 2, minus whatever 7 times 26 is. Pick up your calculators if you would. Calculate, calculate, I'll pause. Alright, I got 1053 minus 182, which is 871 on my calculator. Alright, one more. This is the sum of the, it doesn't start at 1. It's the sum of the 4th through 16th cubes. I'm going to use this formula, but my index does not start at 1. So I'm going to use that trick from up above those properties. I'm going to go from k equals 1 to 16 of k cubed and subtract off the ones I don't need, which is k equals 1 to the previous 3 of k cubed. And then I'm going to plug into this formula. Let me pause and run out of time. Okay, when I plug that index into that ending index into that formula for the cubes, I get this. Pause, plug that into your calculator if you would. I get 18,496 minus 36, which is 18,460. Thank goodness for some formulas up above. All right, ladies and gents, homework tonight, or homework for today, please submit a picture of your completed 7-1 worksheet, the front and back, to this assignment, the 3/17/20 assignment on Canvas by midnight on Tuesday. Have a fantastic day, and we'll break out our jerseys for tomorrow. See ya.